Hello. In this video, we are going to discuss the most fundamental concepts regarding programming. Let's call it Programming 101. Come with me. If we look at the definition of computer science given by the Encyclopedia Britannica, we see that algorithmic foundations lies at the heart of this definition. In fact, it's quite difficult to imagine a computer scientist not involved with the definition of algorithms and programs. But the way a computer scientist thinks is a bit more complex than that. Since 2006 that Janet Wing is discussing this. And so far, what we have developed, what we have learned about how a computer scientist thinks is that it's a combination of four skills. Of course, algorithmic design is the most famous one, and it's actually the one we are going to start develop now in our Python course, in which we develop programs. We write algorithms and then we translate them into a language of a program. But what is a program? Well, a program is a series of instructions to tell the computer what to do. But let's not confuse this with the software running on your computer because that's actually an instance. It's those instructions being put into action. The program itself is the sequence of instructions. And those instructions are written in a certain language. We call it programming language. Well, programming languages are no more than a structured formal language used to produce those instructions to the computers. There are different kinds of languages. So, a low-level programming language is that language that provides little or no abstraction from the way a computer, or let's say the processor, gets instruction. Therefore, it's a language more friendly to the computer and therefore less friendly to us. Those languages are also called machine code or assembly language. In contrast, the high-level programming languages, the most popular ones actually, they provide a strong abstraction from the details of the computer. In most of the case, it seems like we are writing English. They are very similar to natural language, and therefore they make the process of developing a program simpler and more understandable. And it's quite important because the harder it is for you to understand a program, the harder it is for giving maintenance to it. So it impacts cost. And I can tell you, if it wasn't the high level programming languages, most likely wouldn't have that much programs running around. Well, but the problem is a computer can only execute programs that were written in a language it understands. And we have so many different computers, we have so many different platforms, and none of them are similar to English. We need a special software called a compiler. This compiler, what it does is to translate programs written in a certain language into another. What it does, in fact, is to translate programs written in high-level languages that we can understand, that are easier to maintain, into low-level languages that are those understood by the computer. And one interesting thing is that you can compile a program to a certain platform, let's say Intel and Windows, or to a completely different platform like ARM processors and mobile platforms. And that's one of the advantages of the high level languages, that we can translate this into different platforms with little or no modification depending on the language. The compilation of a program is this process of translating a program written in high level language to the machine language. So let's see some examples of the most popular compiled programming languages. A very old Fortran. Objective-C was used by Apple for developing the iOS apps for the iOS platform. Now they use Swift. And we have the special case of Kotlin that we use to develop applications for Android platform, and Java. Kotlin has quite good communication with Java, and what Java has of special is that it's a cross-platform language. So this means that if you don't use any platform-specific framework in your code, you can compile it and then it generates a bytecode instead of object code that's generated by the other languages. What is the difference between the bytecode and object code? Object code is to be understood by a certain platform, so it's platform specific, while the bytecode is is produced to be quickly understood by the Java virtual machine. And that's the trick. You have a Java virtual machine running on Windows, and you have another Java virtual machine running on Linux or on your Android. So the program that you compile to Java bytecode is quickly translated to object code when you run with the Java virtual machine in a certain specific platform. And that makes those languages quite powerful in terms of that you are able to produce software that runs on different platforms. But in contrast with the compiled languages are the interpreted languages. The interpreted language need an interpreter. The interpreter directly execute instructions written in a programming or scripting language, of course. These are high-level languages. So it's like you write a line, and then this line is interpreted, and then it becomes object code, and it's ran in the platform specific. It could be line by line or entire file if it's a script. There are some differences between these two families of languages, but let's first have some examples of the interpreted languages. Among them, who can say JavaScript is not important? No, the web runs on JavaScript. Python, the language we're going to learn in this course, is also an interpreted language. Those languages are usually considered of being a low performance language. So let's try to make a quick comparison between compiled programming languages and interpreted programming languages. Compiled programming languages are said to produce higher performance programs. Why? Because when you compile, you do it in a different moment than the moment that you use the program. Therefore, you can take all the time you need to optimize this compilation process and produce the most optimized code to a certain platform. But let's take the case of Java, and that's why I have this question mark to make it a bit relative. With Java, we compile to a bytecode, not to the object code. So when you run it in a specific platform, there is one more step of translating this bytecode to the code that's run in that specific processor and platform. So it's not that quick, but it's compiled. On the other hand, if you get an interpreted language that is said to have lower performance, what they actually do is that you have this script written in high-level language. If you don't change the script, if you don't turn off your computer and it's loaded in memory, what happens that the first time you run this script, it is compiled. So the next time you run, it's not done again unless you change the script or you restart your computer. So it's not that slow, and the compiler can in sometimes can be not so fast. Yeah, but anyway, there are still performance differences because in a compiled language, as I said, you can take all the time of the world to compile and to produce an optimized bytecode or object code. In an interpreted language, you have to make it very quick because you want to use the software. At the right moment that you want to use is the moment in which it's interpreted and converted, translated to the machine language. So this compilation process is not so optimized. On the other hand, compiled languages are said to be less portable because when you compile, you generate specific platform instruction. That's not exactly the case with Java because Java is smart and you produce a bytecode that's quickly translated to a specific platform. So Java is quite portable. Well, but in the case of interpreted languages, they always have high portability because you get a high level language, which is your script in JavaScript or Python, and it's interpreted and translated to the machine language at the time of use in a specific platform. But that's another interesting thing. Imagine you want to update your software on production. If you want to do this with a compiled language, you have to take it out of execution, so put it offline, and then you update this code and run it again. With interpreted languages, you don't need that. You just change the script, then the environment will realize that the script is not the same anymore and it will compile again. So it's quite easy to update software in production. And that's how the web runs on JavaScript. You just put a new version of your JavaScript there, and the next time someone accesses your website, there will be a new JavaScript that will be compiled in your browser and will run just like that. Which language should you choose? It depends on the problem you have to solve. If you want to know more about the differences between compiled and interpreted languages, you can follow this QR code here. It points to a website in which they discuss more or less 10 to 12 differences between those languages. Well, I said in the beginning that the program is a series of instructions and not the thing running on your computer. The thing running on your computer is a process, which is an instance of those instructions that are being executed on your computer. Okay, in the definition, it said that it's being executed by one or many threads. And that's wow, what is a thread? Actually, a program has not just one line of execution. That can be many happening at the same time. Usually, when we define a program, we focus on one specific sequence, one specific line of execution. But in fact, there are many. Imagine this, you have your processor, your computer. My computer has eight cores, let's say. It could run 8 programs at a time. I have much more than 8 programs running right now. And each one of these programs has many threads running. Think about Word. You're typing your text in the Microsoft Word, let's say. And then if you send it to print, it has to translate this to the printer, to communicate with the printer spooler, send it there, control the operation. So in fact, when you run a process, when you have a process like Microsoft Word running, if you go to see in the task manager, you will see there are many threads. And well, how can you run all of them if you have only 8 cores? That's how the scheduler goes into action. Each operating system has its own, and it also what defines why operating system is better than the other. It's one of the things how they deal with the multitask. So let's see how it is. The program is the set of instructions. So you can see at the left there. This set of instructions are instantiated into the memory. So there is a process running now. This process, as you can see here, process number one has many threads, many instructions, many small programs that are being run at the same time. But we have only a limited number of cores or processors. So what happens is that the scheduler, that is part of the operating systems, it gives a slice of time, a time slice to each one of them. So it's very quick, and for us, it seems like they are happening at the same time. Let's see, I give some time for the thread 1. The thread 1 runs. When time is over, I have to stop it and give the time to another one. But I have to save the state. So this is called context switch. I save the state, the value of the variables, whatever is happening with the program, so that when I put this to run again, when I bring it back, I can restore it at the point it was. So that is a cost for this switch. Okay, but we prefer to have that because in that case we can better use the hardware we have. But don't worry with this very much. For the module 1, we are not going to talk about multi-thread. We're not going to develop multi-thread software. We're going to do this on module 2. But it's important that you know that there are many, possibly many threads running. Although usually we only think about one sequence. All those things we will understand as we get more experienced with programming. Oh, but let's just understand what is a thread. A thread is the smallest sequence of programmed instructions, and they can be managed independently by the scheduler because, well, because they are not so heavy, and it's easy to change from one thread to the other, easier than changing from one process to the other. So all those things have to be managed by the operating systems, and that's why we have so much difference between macOS and Windows and Linux and so on. But that's also something for you to discuss on week 4. So let's stop here by now, And let's discuss the process life cycles. How does thing happen that all those processes are running at the same time? So let's understand this is a very simplified version. You create your process. So you get instructions of the program, you put them into memory. They are ready. So the operating system decides, now I want to give some time to this program, and then dispatches it to running. So when it's running at a certain point, timeout, and it has to give time to another process. So when it's timed out, it goes to the ready state and it's in line to be called again. There is also what we call the block. So the program is running and for some reason it gets blocked. When it gets blocked, it can get blocked because you asked in your program, oh, block it now because I want some sort of sequence in the execution, let's say. Or most of the cases because you are doing an input and output operation. Let me explain. The processor is quite quick. The memory is also quite quick. But if you want to save something in the storage, especially an old one, let's think about a hard drive, which is mechanical. So it takes time. What happens if you do any input and output operation like writing something to the network or sending something through the internet or saving a file into the hard drive or even in the storage SSD? The operating system says, oh, okay, you want to make an input output operation. So I will put you blocked. I will run this operation in background. And when it's ready, I call you again and unblock you and put you online. That's why it's so efficient, because if we have to wait for each input output operation, oh, we wouldn't be able to do what we do nowadays, and we would need many, many, many processors. So that's the trick that makes the multitask in a very, very simple way, because, well, that's not the goal of our course. I just need you to understand how a program works, how it goes into memory, and how it is scheduled roughly so that we can have a fresh start. Wrapping up, we discussed a little bit what is computer science, the way a computer scientist thinks, what is a program. Then we discussed high level and low level programming languages, compiler and interpreters, programs, process, and threads. And finally, a very quick view of the process lifecycle. If you want to practice those things, follow this QR code. That is a quiz, a Python quiz on Canvas. You can already answer the questions from 1 to 10. If you want to also answer the questions from 11 to 15, you need to watch the playlist of desk checks. Or, well, if you are already a programmer or if you want to try by yourself, go forward. See you soon.